Hello, I'm Jordan Aseo.
I'm Elizabeth Gray.
I'm Nicholas Ritter. And I'm Amr Salman, and we present to you characterization of a paint PMMA polymer blend.
So, polymers are large molecules composed of many repeating units, and a polymer blend is formed by simply mixing two or more polymers together. Shown up here is the repeating unit for polymethyl methacrylate, or PMMA, which we use with latex paint in our blend. Both of these are thermoplastic polymers, which means that they can be reheated and reshaped, and this allowed us to mix them into an immiscible polymer blend. An immiscible polymer blend is a physical mixture where mechanical bonding occurs between the two polymers. This means that no chemical bonding occurs and each polymer remains in its own distinct phase. As you can see from the diagram, no matter the ratio of one polymer to another, in this case blue to yellow, each polymer will still remain in its own distinct phase.
The reason we chose to use latex paint for our polymer blend is because with an estimated 17 to 35 million gallons of unused paint left over each year, paint is the single most voluminous household hazardous waste material collected by local governments, and latex paint constitutes 50% of this estimated figure. Financially, this poses a huge burden on the U.S. Municipalities have to pay a minimum of $8 per gallon in order to properly dispose of waste latex paint into landfills. And if all waste latex paint were disposed of properly, this would cost us about $275 million per year. On top of this, since many consumers are deterred by the burdensome process of proper disposal, which consists of leaving the paint out to dry and making sure that no children, pets, or wildlife get to it, latex paint is often improperly disposed of into storm drains and bodies of water. This poses huge environmental concerns because the toxins and pigments found within the latex paint are extremely harmful to fish and other aquatic life. As such, the purpose of our research is to mitigate the negative effects associated with the disposal of waste latex paint, while simultaneously creating a cheaper alternative to pure PMMA by creating an immiscible paint PMMA polymer blend.
We began our research by preparing the latex paint in the PMMA for injection molding. The latex paint was first collected from earth paint collection systems and then was ground into flakes. The latex paint was then put into a vacuum oven at 25 degrees Celsius for 24 hours. The PMMA, on the other hand, was already in the form of granules, and it was placed in a mechanical oven at 85 degrees Celsius and was ran for 24 hours to remove any water molecules that may have been absorbed. The injection molding process is used to mass produce plastics of various sizes, shapes, molds, and designs. This process was ran at 420 degrees Fahrenheit and was ran at 320 RPM to produce our flexural and impact specimens. Using the flexural specimens from the injection molding process, we ran a 3-point flexural bend test following the ASTM D790 standards set by the American Society for Testing Materials. To perform this test, the flexural specimen is centered on the lower supports, and a crosshead running at a rate of 1.4 millimeters per minute exerts a force onto the center of the flexural specimen until either reaching 0.05 strain or until the flexural specimen breaks. From this test, we can determine the stress-strain curve, the stress at yield, the strain at yield, as well as the modules of elasticity.
So shown here is a stress-strain curve which outlines the mechanical properties of polymer. And measured on the y-axis is strain, which is calculated as amount of load with respect to cross-sectional area. Measured on the x-axis is strain, which is calculated as amount of deformation in the direction of the applied force with respect to the original length. And in the elastic region, the modulus of elasticity is defined as the slope of the line. Also in the elastic region, elastic deformation occurs. This is bending that occurs as a result of a load being applied to a polymer. But when the load is removed, all bending will fully recover. Past the yield point though and into the plastic region, plastic deformation begins to occur. This is not recoverable regardless of whether the load is removed. The polymer can still withstand some stress and strain though before ultimately reaching fracture point.
The next test we performed was an IZOD impact test based on ASTM standard D256. We prepared our specimens by notching and measuring them, and each sample, of which there were 2, were composed of 10 specimens each. In order to perform our impact test, we placed a specimen in a vise and swung a pendulum in order to fracture the specimen. By measuring the speed of the pendulum at each point in the swing, we were able to calculate the energy absorbed by the material during crack propagation. This tells us the impact resistance of the material. Differential scanning calorimetry, or DSC, is a method of thermal analysis that involves heating a specimen, cooling it back down, and then heating it back up again. We use DSC to determine the glass transition temperature of PMMA. Below the glass transition temperature, an amorphous polymer will act as a glassy and rigid solid, while above its glass transition temperature, it will behave as a rubbery and ductile solid. In contrast, for the 2080 paint PMMA blend, we used MDSC, or modulated DSC. The difference between MDSC and DSC is that MDSC includes temperature modulations, and what those are is local temperature oscillations that occur even as the average temperature steadily rises. Fourier transform infrared spectroscopy, or FTIR, is a method of determining what type of bonds are present in the material. What happens during the test is that infrared light is emitted into a sample. And as this light is emitted at varying frequencies, the percent transmittance is recorded. We use this data to determine the chemistry of the material.
After collecting and analyzing our results, we were able to generate a stress strain curve for each sample. According to ASTM standards, at least 5 specimens must be tested for flexural testing. For our paint PMMA sample, however, we tested 7 specimens to verify our results because 2 specimens broke as a result of contaminants found in the paint. If we take a look at figure 12, one representative specimen was selected to best represent our data. At the end of the curve, the stress at yield can be found, which is an indicator of the flexural strength of the material. The red curve, which represents a 2080 paint PMMA, is actually below the blue curve, which is a PMMA, and thus the flexural strength of the paint PMMA polymer blend is less than that of the PMMA. Transitioning to the table, the modulus of elasticity is shown. Modulus of elasticity is an indicator of the material's stiffness. Since both values are the same, 3.1, the stiffness is retained in the polymer blend, even though a waste latex paint was incorporated in it. The IZOT impact test was performed to measure impact resistance, which is the energy absorbed upon impact. If we take a look at figure 13, the blue dot representing the PMMA is slightly higher than that of the paint PMMA. However, something interesting that we want you to take note of is that the impact resistance of the paint PMMA actually falls within the standard deviation of the PMMA.
Using DSC, we determined that the glass transition temperature of PMMA alone was approximately 106 degrees Celsius. However, in the blend, the glass transition temperature of PMMA was decreased by approximately 9 degrees Celsius. The second peak, labeled paint in figure 15, is the glass transition temperature of the paint in the lower temperature range. The FTIR results of latex paint and PMMA showed that they had similar bonding, which makes them a good candidate for forming an immiscible polymer blend. Secondly, you'll see that the red line is the paint PMMA, and it has characteristics from both of the original materials, latex paint and PMMA, which shows we did in fact have and achieve an immiscible polymer blend. Finally, not shown in this graph, across 3 samples of the 2080 paint PMMA polymer blend, using FTIR analysis, we determined that we had consistent composition and good mixing because all 3 of the FTIR spectra were very similar.
So here's just a summary of the significant results that we got from each test. From Flexural, we found that both the paint PMMA and PMMA shared roughly the same amount of stiffness, but the PMMA did have a higher stress at yield. This is perfectly fine though, because our blend is created from a waste material, and so it doesn't need to necessarily match the properties of pure PMMA. Also pictured here are the fracture surfaces from the specimens that broke, and as you can see there are some white specks. These are contaminants that are basically unwanted material that was recycled along with the latex paint that we can't really control. And these were the most likely cause for the fracture that occurred. For impact testing, we found that the impact resistance of the paint PMMA blend was within the same region of the PMMA. And this may even increase if we can somehow find a way to filter out the contaminants prior to molding. From thermal analysis, we found that adding the paint into the PMMA lowered its glass transition temperature by about 9 degrees Celsius. And contaminants may also be a contributor to this lowering. Finally, from FTIR, we found that the paint and PMMA both have similar chemistries, which make them good for the blend. And the paint PMMA blend that we created has consistent composition.
So we set out with our research to create and determine the properties of a 2080 paint PMMA polymer blend, which we were successfully able to do. For one, we melt process the waste latex paint with pure PMMA to create our miscible blend, which was evidenced by the uniform gray color we achieved throughout all of our specimens, as well as the consistent results we got from FTIR testing. From our research, we also obtained very similar values for flexural modulus and impact resistance, which shows that despite the addition of a waste material, that being the latex paint, many of the mechanical properties of the PMMA were largely preserved. This has positive implications for future use because the similarity of the two materials' properties means that paint PMMA can be used as a cheaper alternative to PMMA in many of its applications. However, further testing and analysis needs to be performed in order to better understand the characteristics of our composite. In addition, further tests needs to be performed in order to see how paint acts with other polymers and in other ratios to see what kind of polymer blend is the most efficient for recycling waste latex paint. Finally, further tests need to be performed in order to determine what is the most efficient way of removing the contaminants from the latex paint so that way the composite's mechanical properties are not compromised as a few of our specimens were.
This research project could not have been done without the help of many, so we'd like to especially thank our research mentors, Dr. Jennifer Lynch and Jamie Wooding, our RTA, Kelly Rupernak, also the director of this program, Dr. Eileen Rosen, and the associate director, Dean John Patrick Antoine, and also those that helped us in the lab, including Emily Danilak, Dr. Thomas Nosker, Arya Tawatia, and Ryan Zito. We'd also like to thank Rutgers School, the State University of New Jersey, Rutgers School of Engineering, and also the Governor's School Program, and all our other corporate sponsors for making this possible. You will now be taking questions.
So the purpose of this project is to try to recycle latex paint and make it into PMMA.
Well, paint and PMMA are two separate materials, PMMA being the kind of polymer. The latex paint and the PMMA have very similar chemical compositions, and as a result, we can mix the two materials together to create a blend that we could use for just pure PMMA applications.
So then the sample you took would be like a latex paint already like in a solid form. Do you have to make it into a molten form so you can extract the contaminant?
Well, yeah, we collect waste latex paint that people don't want to go through the hassle of disposing. So we take the solid latex paint, we grind it up, and if you remember injection molding, it's pretty easy. You just mix them, just take both of them, put them in the ratio that we wanted, and dump it into the injection molder, and that does all the heating and uniformly distributes them into one blend.
So you're using mechanical force to blend it, not to melt it or make it a molten form.
Well, yeah, there's a rotating screw which creates friction, and there's heating bands that help the dry, like solid granules and dry paint get mixed into one molten blend that then gets shot into a mold, and that's where it cools into the specimens that we wanted to use for testing.
Yes?
You mentioned that the temperature of the PMMA in presence of paint goes down or it's lowered by 9 degrees or so. What is the significance of the TG? What is the consequence of that?
Well, the significance of the glass transition temperature is that there's either not enough or enough thermal energy to have significant bond rotation or molecular movement. But the actual significance of the glass transition temperature in PMMA's applications, you'd have to look at specific applications.
Aside from the recycling benefits, you also mentioned that blending the paint and the PMMA will actually reduce the cost for the application of what PMMA is used for. Do you have a sense as to how much that cost is actually reduced, the relative cost of the PMMA versus blend?
Well, there's no exact cost. That's something, a lot of studies are going to have to be performed on that. However, it is definitely less inexpensive to include the waste latex paint into the PMMA blend because the latex paint, it is waste. So, I mean, it's also reducing the financial burdens that are put on properly disposing of the latex paint because, as we said, it costs at least $8 to properly dispose of this latex paint, and that can cost up to $275 million per year.
And in addition, for each municipality, it costs them a different amount of money to actually dispose of this latex paint. So you have to look case by case, but we do have those national statistics that Elizabeth mentioned before. Yes?
PMMA, my understanding, is supposed to be transparent on the glass, so once you add paint to it, what color would it be?
So what we did was when we mixed the latex paint, we also added carbon black, so it had a uniform dark color. Now, there are actually a lot of applications for this dark color. For example, laptop casings, generally electronics casings, as well as appliance housings.
What is the current proper procedure for discarding paint?
Well, do you want me to? I can take that. You can't really dump liquid paint into conventional garbage trucks because they'll contaminate everything and make it really messy. So you have to go through the annoying process of drying it basically in your home or in your backyard, drying it, then bringing it to a special place that takes care of toxic materials, and then you just take your dried paint, bring it there, and then they have to recycle it for you. So you can't just dump it into a garbage can.
Ask my question correctly. So how do they properly take care of it for you? I mean, from the time when you give them the dry paint, what do the government agencies do with it?
Well, they bring it along with the other hazardous materials. Our research project didn't go as far as knowing what they do with all the hazardous materials after the consumer brings it to there because governments just handle it. So I'm sure they have a safe place to put the dried latex paint.
So I know you said the presence of contaminants may affect the results of your tests. What steps would you take to reduce the number of contaminants in your lab?
That would be a matter for future research. The scope of our research was to characterize the actual properties of this polymer blend, the paint PMMA blend. But as Elizabeth said in the future research slide, we would need to investigate more as to the best way to filter out those contaminants that are put in by consumers while they dispose of paint.
Last question.
So your project, the purpose is part of is to eliminate the burden that we have to dispose of those used paint. Have you ever done any analysis, cost analysis, your process, how much you have to spend on per gallon?
Per gallon for disposal?
No, for your process.
For our process, well, the injection molding process itself is actually very common in industry, and you can mass scale it. So often, if you're scaling, it's going to be less expensive. And so both those processes can be used for PMMA and the 2080 blend. The scope of our research doesn't go into cost analysis because we simply haven't determined the best blend yet. It simply characterized this potential mechanism for recycling latex paint.
Thank you.